All right, good day, everyone. What we're going to be focusing on today is reciprocal trig functions, okay? So we're going to be looking at the three other trig functions that go along with sine, cosine, tangent. Those are secant, cosecant, and cotangent, all right? Each of these are the reciprocal versions of themselves, okay? So one of the things to kind of understand, and first off, is what this idea of reciprocal and what it really means, okay? To kind of put it in perspective, something that's reciprocal is just a flipped version of that fraction. So an easy way to look at this is to say if you had 2 over 5, the reciprocal of that would be 5 over 2. Okay, so each of these functions are the reciprocal versions of their counterpart. Okay, so let's kind of talk about what that represents. The three that we have talked before, we talked about them in the other lesson, is what sine, cosine, and tangent represent. Well, sine is the value of the opposite over adjacent, opposite over the radius. So you have y over r. Cosine is going to be your x over r, and your tangent is going to be y over x. Well, each of these values have reciprocal of the original. So the opposite, or I should say the reciprocal of a sine, is a cosecant. So cosecant is just the radius over y. The reciprocal to a cosine is just secant, which is just going to be the radius over x. And then the reciprocal to a tangent is cotangent, which is just x over y. So each of these values are the same exact concept. It's just the reciprocal versions of themselves. Okay, that's why that fraction and understanding the r's radius and then what the values go with which are so important. Okay, so let's talk about how this actually works. Knowing that we can find like sine, cosine, tangent on the unit circle, we can actually sit there and solve for cosecant, secant, and cotangent. Okay, all we really have to do to change this is to understand what the reciprocal version is. So the idea of secant is that secant is the reciprocal to cosine. So if cosine is x over your radius, this is going to be the radius. This one's going to be the radius over x. So how we could solve this out is we're still going to go to the 45-degree mark. We're still going to focus on the x value there. But now instead of plugging that in on top, this is going to turn into 1 over the square root of 2 over 2. Which, if we're dividing by fractions, we could simplify that into 2 over square root of 2. And then from there, we basically just have to get it in a better form. So we're going to multiply square root of 2 on top on each side. That would give me 2 square root of 2 over 2. And then the 2's cancel out to give me a final answer of a square root of 2. Okay? So notice it's the same concept and the same idea as we've been taking before. The only difference now is that when I actually plug that value in, I'm going to come up with a specific value. In this case, when I plugged in square root of 2 over 2 and got out my final answer, it came out to be just an answer of square root of 2. Okay? Once again, that's the reciprocal version of that answer. Now, let's talk about what happens. What do we do with a cotangent? How do we actually deal with cotangent? Well, cotangent now is almost the same idea, all right? It's the opposite of our original tangent function. Now, if tangent is y over x, cotangent is going to be x over y. Meaning, if I look at 2 pi 3, so if I clear this off, and now I'm focusing on 2 pi 3, which is right there, I'm going to take my x term and divide it by my y term. Well, this is just negative 1 over 2 divided by square root of 3 over 2. Well, when I divide out fractions, I skip, flip, multiply. So I'm going to skip the first term, flip the second term, and then multiply it out. The 2's will cancel, and right now I'm left with negative 1 over square root of 3. And if I simplify that by multiplying square root of 3 on top and bottom, I'm left with a final answer of square root of 3 over 3. And do not forget the negative, okay? So understand that it's the same exact math as what we would do before, right? Because if we had a tangent, we would just do y over x. And we'd be following the same exact steps to simplify. The difference now is that as I'm working it out, as I'm simplifying it, I have to understand that we're dealing with the reciprocal versions of the original. So instead of saying like cosine of x equals this, a secant of x is going to just be cosine flipped, okay? So why is this important? Okay. Well, Understanding how to get these answers is important for the simple fact of when we're dealing with like a secant of 270. Because this is where the reciprocals become very interesting. 270 is here, and secant has to deal with my reciprocal of cosine. So once again, I'm going to be dealing with the radius over the x. Well, if you consider at 270, x is equal to 0, and the radius is just 1, technically it would be 1 over 0. Well, this is a problem, right? So we have to understand that the reciprocal of our original can be undefined at certain points. In this case, the secant of 270 is actually an undefined function for the simple matter that I can't divide by a 0. Now that's interesting in the overall fact that a cosine function basically is a periodic function. It always repeats, it's always continuous, it never has an asymptote. While a secant function has specifically an asymptote at wherever x equals 0, which is going to be 2 points on the graph, 270 and 90. Okay? And that's just one of the interesting things that we want to kind of take in and understand, especially as we're moving forward. Okay? But that kind of leads us into the second part of this section, which is basically an understanding of how can I take a standard coordinate and basically be able to label out each and every value from that. Okay? The whole idea is this, is that if I'm given a coordinate, technically I have an x and a y, right? In this particular function that I had an x equal to 4, a y equal to -3. Well, if that's the idea, if I find my radius, technically I can label out any and all of the functions given. So if you notice what they did here is they actually worked it out using Pythagorean theorem to solve out to find the radius. And then they have all the values to solve out sine, cosine, tangent, and cosecant, secant, and cotangent. So let's say we were given a very similar problem. Let's say we were given P where it's -5 and -12. Okay? Well, first and foremost, let's go ahead and find our radius. If I have a P of -5 and -12, that tells me x equals -5, y equals -12. And now I just want to figure out what is my radius of the function. Well, to solve that out, I need to do Pythagorean theorem. So we go -5 squared plus -12 squared, and that has to equal my radius squared. This comes out to be 25 plus 144 equals r squared. And then that's just 169 equals r squared, and then r squared is going to come out to be, or r is going to come out to be 13. Okay? So we know we have x is -5, y equals -12, and r equals 13. So now if I wanted to label out all my different values, let's say I wanted to find my sine value. My sine value of whatever theta is going to be equal to my y over my radius, which is going to be -12 over 13. But now if I want to find the reciprocal of that, which is cosecant, it's going to be that same sine value, but flipped. It's going to be 13 over -12. If I want to find my cosine value, it is x over my radius. So cosine of theta is going to be my x value, which is -5 over 13. And then the reciprocal secant is just going to be the flipped version, which is 13 over -5. Last but not least, we're going to deal with tangent. Tangent's my y over my x. This would just come out to be 12 over 5. Notice how I could have wrote -12 over -5, but the negatives would have canceled out, so they become positive. That's going to be an important idea to remember moving forward. And then my cotangent of theta is just the flipped version, which is just 5 over 12. Okay? So by having those three values, especially when I have a specific coordinate, I can basically solve out and find all 6 different trig and reciprocal trig functions within a polynomial, or excuse me, within a problem like this. Okay? But we'll talk about the rest of this lesson within class tomorrow. If you have any questions, bring them in and we will talk about them. Besides that, have a great day.